All right, so welcome to our kind of third topic here in chapter 14. Even though I know it's not necessarily a third lecture, but what we're going to be moving into kind of now is taking a look at some other things that affect reaction rates, in particular temperature. And so we're going to be talking about kind of what happens both from a kind of a conceptual aspect and then looking at kind of what's the math side of things and kind of the equation that we can use to model this effect as well. And in general, the thing that we're always going to notice is that the reaction rate is going to be temperature dependent, no matter what. There's pretty much no way around that at all. If you change the temperature of reaction, the rate of it's also going to change. And probably the biggest thing you'll note is as your temperature increases, reactions will actually always go faster. That is something that no matter what should happen. And from kind of a molecular picture in terms of why that happens, as your molecules move faster, there's going to be more collisions between those molecules that have more energy. And one of the things we're going to see here in just a moment is that for basically any reaction to happen, you need to have molecules collide, and they need to have enough energy when they collide to cause a reaction to occur. So more collisions with more energy means it's more likely to have collisions with enough energy for the reaction to happen, which means the reaction should go faster. That's kind of the just, I guess, quick molecular picture of why higher temperatures should cause faster reactions. And the other aspect of this is we have this what's called activation energy for all of our reactions. And that's why I said that we have this kind of energy barrier that needs to be overcome. We need collisions to have a certain amount of energy when they occur in order for a reaction to actually happen. Because just particles colliding, even if they're the right reactant molecules, doesn't always guarantee that any reaction is really going to happen. So to give kind of a visual image of this is a pretty common type of diagram. It's called like a reaction energy diagram that you'll see in this chapter and also probably even in the next chapter as well. And really all this is showing is here's our reactant starting out. They're at some potential energy initially. And then as our reaction progresses, in order to go from our reactants to our final products, we have to typically go through what's called a transition state. So the transition state is usually a higher energy, less stable kind of configuration of everything, of all your reactants. That's kind of on the way to getting towards your products, which may or may not be, at a lower energy than where you started for your reactants. For this particular energy diagram, since the products end up at a lower energy than our reactants, this would be an exothermic reaction. There is some energy we have to put in initially to overcome this kind of what's called activation energy barrier. That's that E sub A kind of abbreviation you see here, stands for the activation energy, which is where our reactants started out energy-wise up to the top of this little peak to get past the transition state of our reaction. And then we get to our products, which are now way down here on the other side. And since the products are lower in energy than the reactants, that's what's making it exothermic overall. Uh, but this is why, even though this is an exothermic reaction, this is why you can't just put two reactants together and expect an immediate reaction, even if it's exothermic all the time. Because there is this activation energy barrier that has to be overcome. And you might have an exothermic reaction, but if the activation energy barrier is really, really big, you might not get much of a reaction, or you might not get a very fast reaction to actually make your products for that exothermic reaction. So, where and how do we reason through how temperature plays a role in this? Well, temperature is going to play a role, and similar to kind of some other things we've seen here in the last couple chapters, it's not a nice, easy, linear relationship. And the reason for that has to do with kind of how the energy of particles is distributed due to temperature. And so we have what's called here some Boltzmann distributions again, in terms of, here we have at a lower temperature, here's at a higher temperature. And what these plots show, the blue line here for our lower temperature, these are going to show our energy, basically, of the particles. And how many, I'm sorry, this is actually the number of particles on the y-axis, sorry. Then the energy those particles have is actually being shown on the x. So at a lower temperature, most of our particles are at a lower overall energy. There are some at a higher energy, but if this is where our activation energy is, there's only a small, tiny percentage of the particles that are actually able to make that reaction happen. But as our temperature goes up, this curve kind of flattens out more. And what happens is now, like, we have fewer particles at this lower temperature, although it's still where most of them are as the lower energy. I shouldn't say lower temperature. At the higher temperature curve here, there's fewer particles at the lower energy, and there's more particles out here at the higher energies. Which means if this again is our activation energy kind of cutoff, there's a higher percentage of particles out here under the purple line than what there was under the blue. So the higher temperature has more particles with enough energy to cause a reaction to happen. But again, it's not a nice linear relationship because these are pretty common shapes for particle distributions as far as their energies at different temperatures. So it's not that linear relationship that we would normally like to see. Thankfully, the equation actually looks pretty similar, though, to something we have been seeing and using over the last couple chapters. And so the actual relationship between temperature and the rate constant is going to be shown through what's called the Arrhenius equation. And the Arrhenius equation has a couple different versions. But again, we do want to pay really close attention to units. So a couple things here. Temperature has to be in Kelvin. Energy, you probably want this in joules, which means the R is going to be, the 8.314 version of the ideal gas constant. But this is kind of our generic version of the Arrhenius equation. Our rate constant K is equal to a capital A, which I'll get into a second. In a second, I'll get into kind of what that is, times E to the negative activation energy over R times T, where R is that ideal gas constant and T is that temperature. So most of these things, like the rate constant, temperature, the ideal gas constant, are pretty familiar. The activation energy is new, but it is what we just talked about. And then A is kind of this weird part. It's called that collision frequency factor. So it's not that easy to actually get A, and it's not something you're just going to know offhand for any given reaction. You have to experimentally find it, so it's kind of a pain to calculate most of the time. And what it really accounts for, though, and like why it's in that equation, that's the part that accounts for the fact that not only do your reactant molecules need to collide with enough energy, but they also need to collide with the right amount, with the right or correct orientation. That means if you have two molecules that are like kind of chain-like structures, if they hit each other head-on, they might react. But if they hit each other like side-on, like with the long chains kind of slapping against each other, like they might not react. And so there's an orientation factor to those collisions as well in terms of the reaction being able to happen. And that's really what this collision frequency factor is kind of accounting for in that equation. Now, for us, we probably won't actually even use this version of the equation all that often. Probably the version of the equation that we will be using more often is going to look similar to things that we've actually seen previously. Because this equation, we can actually rearrange, like if we want to get rid of this like e to a power, so that we have like temperature in kind of an easier access way, then one of the things we can rearrange this to is an equation where it's the natural log of k is equal to negative EA over R times 1 over T plus the natural log of A, which is a y equals mx plus b form. And hopefully this looks familiar. It probably looks pretty much exactly like the 1-point form of the Clashes-Clapeyron equation that we saw back previously at the end of chapter 11. And that's pretty much exactly what this is. There's almost no difference. The only difference in the equation is instead of having a vapor pressure over here, we have K, a rate constant. And instead of having enthalpy of vaporization, we have an activation energy. Otherwise, this equation is the same. And if for the Clashes-Clapeyron we had a 1-point form and a 2-point form, that actually means for the Arrhenius equation, we can also have this 1-point form, but we are also going to have a 2-point form to go with it. So in lab, something like this is going to be useful. You'll actually be using this type of equation to make a plot in lab when we do our kinetics lab. I think it's the end of this coming week is when that's in our schedule. But in lecture, we're probably going to be using the 2-point form of the equation, right? Which is going to be this one down here, which looks almost identical to what we saw for the Clashes-Clapeyron. For some reason, I've seen a lot of textbooks that prefer to write this equation this way for this particular equation, where there's a negative sign out in front. I probably usually, when I write this equation myself, I usually don't have this negative sign here, and I switch the T1 and T2 as a result. So if you see me, it's like, oh, where's the negative sign? Well, pay attention to whether T1 or T2, like what order they're in. I usually do 1 over T1 minus 1 over T2 so that there's no negative sign here. And that's also the exact same way that I had the Clashes-Clapeyron equation set up previously, right? Otherwise, this equation hopefully looks pretty much the same in terms of the algebra and things involved. We have rate constants, Ks instead of the vapor pressures, activation energy instead of enthalpy of vaporization. The rest is pretty much the same. If I wanted to, I could break up this little part here and have it as the natural log of K2 would be equal to like the natural log of K1 if I moved it over, minus all of this, or natural log of K1 plus EA over R times 1 over T1 minus 1 over T2 for kind of the order. So it is really the same equation, just Ks instead of Ps, EA instead of HVAP. So hopefully using that equation is not going to be anything really new. Now, if we want to work an example to use that equation, Here we're told we have a reaction where the activation energy is 487 kilojoules per mole, and we're told that the rate constant is 2.10 times 10 to the minus 3 at 300 Kelvin. And then we want to know, what is the rate constant going to be at 350 Kelvin? So for using this Arrhenius equation that we just saw, again, 2-point form is what we're going to use almost exclusively in class or for exams or for homework, things like that, because I'm not going to be having you make a plot as part of your exam. It's just too time consuming to do that. So what we're going to be doing is just looking for our pieces. We have an activation energy, we have a rate constant at one temperature, and we're looking for a rate constant at a different temperature. So we basically have, this would be like, K1, T1, this would be T2, we're looking for K2, and we have the activation energy. So we pretty much have all of our pieces to be able to just go through and solve for K2 in this case, because R is just a constant, it's the 8.314. And so really it's just now plugging in all of the actual math components. Now, I'm going to show this one way here on the slide, and then I'm going to put it on like a whiteboard example of kind of going through it maybe in a way that you're maybe more used to. But what I did here on the slide is I actually rearranged for the K2 just by itself and kind of showed some of the math steps that we can go through to do that. If you don't want to do all this rearranging in math, which honestly, if you have a scientific calculator using for most of this, this is maybe not the best way to do it. You're better off just taking everything as numbers and kind of slowly breaking it down and doing the calculation, which is kind of how I'm going to do it on my slide here in just a second, or on my kind of like whiteboard here in just a second. And so I'm going to back up one step and then go and pull up whiteboard. All right, and so what I want to be able to do is use that 2-point form, but I'm going to use it in this version. Right, that's the version or how I normally write it. This should look almost exactly like the Clash as Clapper way we wrote things as well. And now I want to make sure things stayed paired together properly. Right, so K2 is what I'm looking for. K1 and T1 are the pair that we know the rate constant for. So if I go back to my problem, here we see that my K1 is 2.1 to the minus 3, and T1 is 300 Kelvin. So if I plug those values in, I'm going to have the natural log of 2.10 to the minus 3 plus the activation energy, which was 487 kilojoules, which is 487,000 joules per mole, right, over R, which is 8.314 joules per mole Kelvin. And notice I made sure to put my activation energy in joules since R is in joules. You could also put R in kilojoules and leave this as 487 kilojoules per mole. That's also fine. Either one will work just the same. And then T1 I said was 300 Kelvin, so 1 over 300 Kelvin minus, I want to know the rate constant now at 350 Kelvin was, I think, the new temperature, my T2. I'm just going to double check that. Yes, 350 Kelvin is what we're looking for. All right. So at this point, if I'm solving for K2, and if you have a graphing calculator, a lot of this becomes much easier. If you have a scientific calculator, I would be very careful about trying to do this all in one step just because there are a number of parentheses. So for instance, if I had a scientific calculator, I would just be doing this kind of one piece at a time. So I can go, for instance, go ahead and do, let's see, I can do the natural log of 2.10 times 10 to the minus 3. Which I get as negative 6.17 plus I have 487,000 over 8.314. Which I get to be about 58,575.9. This is going to be like 1 over Kelvin for units times Nope, it's actually not 1 over Kelvin for units. It's actually just Kelvin for units, because Kelvin's going to cancel here in just a second for my units. Now I have 1 over 300 minus 1 over 350. And I get this to be about 4.76 times 10 to the minus 4th. And that's going to have units of 1 over Kelvin if I care about the units. So my 1 over Kelvin here and my Kelvin here will cancel. And now I can kind of start putting all this together. I'm negative 6.17 plus. I can multiply this chunk out. So I'll have that 4.76 to the minus 4th times that 58,575.9. And I get about, let's say, negative 6.17 plus positive 27.9. And all of this is equal to the natural log of K2. And so now I can combine the last pieces on this side of my equation. So I can get about 21.7 roughly. And that's my natural log of K2, which means K2 is going to be e to the 21.7 power. And that is positive, so it's going to be a really big number. So I'm going to have e to the 21.7 power. It looks like I get about 2.66 times 10 to the 9th is going to be my K. Now, the last part of this, my units on this rate constant, if I go back to my original problem, my units were inverse seconds. So my units are going to be the same for this rate constant as well. So inverse seconds, sorry, for my units there. That would be then my final answer. And so we actually see that our rate constant went from being pretty small to huge in just 50 degrees. And the bigger your activation energy is, because this is a really big activation energy, the bigger your activation energy is, the bigger the changes in your rate constant with temperature. The smaller your activation energy, then usually the smaller changes you're going to see in your rate constant with temperature. It's kind of some general trends. Now, one thing you can always pay attention to after going through the algebra here, always make sure things at least went in the right direction. So in our case, our temperature went from 300 to 350, so the rate constant should get bigger, so reaction should be getting faster, and we did. We went from something that was times 10 to the minus 3 to something that's 10 to the positive 9, so a pretty big increase. And so that's kind of the main check you want to be making there, just to make sure you're kind of going in the right direction for things. And I believe, looks like here, so this looks slightly different, 2.73 to the 9th. A lot of that's probably rounding, and when you're doing exponents, small rounding differences can make some pretty big differences. So like on an exam or something like that, like if it's like 2.7 versus 2.6 to the times 10 to the 9th, those are going to be correct. I'm not going to be counting off on those kind of roundings because there's a lot of little things that can go there into that that can make some pretty noticeable differences. All right, so the last bit of this little section I do want to talk about is catalysis and what catalysts do to equilibrium, or not equilibrium, to kinetics. We'll actually talk about equilibrium in the next chapter. So for a catalyst, what a catalyst is going to do is a catalyst is something you add to a chemical reaction that doesn't change what your overall reaction is, but does speed up the reaction. That's the end goal, is we want a faster rate for our reaction. So how does it do this? Well, it does this by adjusting what's called our reaction mechanism. So instead of our reaction taking place in a certain way, it's going to change kind of what the individual steps of kind of our overall reaction actually look like. In a way that's going to make our reaction happen faster. In particular, the new path basically our reaction is going to happen by is going to have a lower energy transition state. So effectively what happens is the activation energy is lowered, and that means that if the activation energy is lowered, based on the Arrhenius equation that we just saw before, the biggest effect of that is that our reaction will be faster, or our rate constant is bigger. So to give some kind of visual images of this, here would be kind of the reaction. There's like an energy diagram that we saw, a couple slides ago. If we add a catalyst to this reaction, what changes is, instead of having one single hump, maybe we have multiple humps, but they're shorter, they're smaller. right? The activation energy is a lower value here with the catalyst than what it was without. And so even if there's multiple humps here, the significantly lower activation energy will actually lead to a reaction that's considerably faster in terms of how fast it can get to the product side of that reaction. So that's the main application of catalysts. They're basically just ways to get to the same final products from the same starting reactants, but trying to do so through a different pathway where there's a lower activation energy, which means it will actually get to that product or get to those products at a much faster rate. And we'll talk a little bit more about catalysis, and we'll actually talk a little bit more about this idea of mechanisms and like how do we go from reactants to products, because it's not always like a one-step process for most reactions. And that'll actually be the last little segment that we look at from this chapter that we're going to get into next. And so the last thing I will have one last bit on catalysts here to wrap up with, though, is looking at the types of them, like homogeneous and heterogeneous. So if we have a homogeneous or a homogeneous catalyst, all that means that the catalyst is in the same physical state as the reactants. So as an example, if you have a reaction between gases, the catalyst is also a gas. A heterogeneous reaction is one where the catalyst is in a different physical state than the reactants. And so an example here would be is if you have two liquids or two gases that you want to react, and your catalyst is actually a solid of some sort. And it turns out heterogeneous catalysts are actually much, much more preferred from an industrial standpoint. And the reason for that is if you design a reaction and if you're trying to make large amounts of a product from like an industrial, for an industrial process, one of the things you can do, let's say your reactions between two liquids, you can actually set up these reactions where you flow these liquids through tubes that actually have your catalyst basically on the wall of the tubes. And so your catalyst is actually fixed in a place where as the liquids pass through, they're going to have access to the catalyst, they're going to react, your reaction occurs, your liquids keep passing through, and hopefully you can isolate your product as they come through, but the catalyst stays behind to be able to continue to catalyze further reactions. Likewise, you could also even imagine a simpler thing, like if you're just doing a reaction in a beaker, if your catalyst is a solid, once your reaction is done, your solid is hopefully still there to just be, your solid catalyst is still just there to be able to be reused, because you hopefully just filter it out. And so heterogeneous catalysts usually heavily preferred, just because it's usually much easier to recover your catalyst and reuse it than it is if you have a homogeneous or homogeneous catalyst that's in the same physical state. So that's something I do want to kind of point out there, and that heterogeneous catalysis, that's really kind of the goal for a lot of things, because from an engineering standpoint, it just makes things much more practical when you're trying to do reactions on an industrial scale level, which is like very, very large scale. Like when we're in the lab, we're usually measuring things out in like milliliters and grams. Industrial level, we're talking usually like liters and gallons or kilograms of stuff that we're trying to either make or use. So much larger amounts of materials. So to do things on that scale, heterogeneous catalysts are just going to make that process usually much easier. All right, but that's all I have for this segment. We'll get into, like I said, our last segment here shortly on our reaction mechanisms to wrap up.